Good morning, everybody. This is again Dr. Jingbo Louise Liu. Today we start our chapter 13. In the chapter 13, we are going to be discussing the properties of mixtures. These mixtures involved in two types, the solutions and the colloids. We are going to study 7 different topics. The first one, the types of solution. Based on your solutions, so you can determine whether the intermolecular forces involved in or not. Therefore, you can determine the solubility of your solute, which will be dissolved in the solvent. The second one is still we are involved in the intermolecular forces. When you study different chemicals, so you are going to discussing ionic compounds dissolved in solution, covalent compounds dissolved in solution. In that case, you can determine what is the intermolecular forces between your solute and the solvent. And then we are going to briefly understanding the solution processing. And then we discussing a very important law called Henry's law. Henry's law showed you the like dissolves like, and also what's the solubility of the different gases. And then we're moving on to the concentration terms. This concentration terms is our important topic. You are going to learn 5 different concentration expressions. And then we study the properties of your solution, which is called colligative properties. Also, we are going to learn the properties of the colloids. First of all, let's define the 2 different mixtures. So we already know the mixture is the substances which composed of 2 or more groups of different substances which physically mingle together. Your solution is a homogeneous mixture. The solution exists as a single phase, meaning the particles in your solution are individual atoms, ions, or very small molecules, such as can be oxygen, can be sodium plus, chloride negative, can be your sugar molecules. So remember, there's only one phase. You are not going to see a boundary. The colloid is a heterogeneous mixture. Hetero meaning different phases. So this colloid exists as 2 or more different phases, which may be visible to our human physical eyes. You can visibly distinguish them. The particles in the colloid are usually macromolecules or some aggregations of small molecules. Usually this colloid, the dispersing substances, the one dispersed in your dispersing agent. So that size is ranging from 1 nanometers to 1,000 nanometers. The particles in this colloid, so is going to exhibit some special properties. One is called Dando effect, another one called Brownian motion. Dando effects and Brownian motion. Regarding the solutions, you want to determine whether a solute is going to be dissolved in a solvent, such as if you have your methanol, CH3OH, you have your water, whether these 2 molecules can be dissolved in each other or not. How do you know? First of all, let's define 2 components. Your methanol is your solute. Your water is your solvent. What you are going to see, your water molecules, they are going to form hydrogen bonds. Yeah, thank you, hydrogen bonds. Your methanol molecules also forms hydrogen bonds. And your water molecule and methanol, your hydrogen from your water, the hydrogen from your water, and the oxygen from your methanol, they are also form hydrogen bonds. Therefore, these 2 molecules, they're both polar molecule. they can form a strong hydrogen bond, meaning the methanol can be dissolved in water very well. So this rule called like dissolves like. Let's predict some solubilities of the different compounds. So we have 3 different groups of questions. The first one, sodium chloride, NaCl, sodium chloride. If you dissolve sodium chloride in methanol, sodium chloride dissolved in propanol, which one dissolves more? Second question, you have your ethylene glycol. This is a OH, CH2, CH2OH. You see there are 2 OHs. In hexane, hexane is carbon, 6 carbons, and ethylene glycol glycerol dissolved in water. Which one dissolves more? The third question, this is called diethyl ether. This molecule is called diethyl ether in your water or diethyl ether in your ethanol. So what's your plan? First of all, you are going to examine the molecules of your solute, such as sodium chloride, ethylene glycol, diethyl ether, and your solvent, such as your water, such as your hexane, ethanol, and isopropanol. So you are going to examine those molecules, and then you are going to determine whether there are some forces in the solute or between the solute and the solvent. If your solute has something similar to your solvent, or if your solute in the solvent which can form a strong intermolecular forces, the solubility will be high. So let's see. Solution, your methanol and propanol. Let's see, sodium chloride is an ionic compound. Therefore, it's going to be dissolved in more polar solvent through ion dipole intermolecular forces. Between your methanol and propanol, which one is more polar? So we know OH is a highly polar group. This OH group is a very highly polar group. Your hydrocarbon portion, your CH3, CH2, CH2, this one is called a non-polar group. Therefore, so your methanol is a strong polar molecule, can form a strong ion dipole intermolecular forces with your methanol. Your methanol will be dissolving more sodium chloride. Second question. Ethylene glycol in hexane, ethylene glycol in water. Your water dissolves more. What's the reason? Your ethylene glycol, you have 2 OH groups. Those OH groups is going to be interacting with a hydrogen, which is directly covalently bonded to your oxygen from water. Therefore, your ethylene glycol, OH, and your water hydrogen, they are going to form strong hydrogen bond. It's a very strong hydrogen bond. So therefore, you form strong intermolecular forces. Water dissolves more ethylene glycol. If you have your ethylene glycol and your hexane, you can form something we call the dipole-induced dipole. This intermolecular forces is much weaker. Therefore, hexane dissolves much less ethylene glycol. The third one, diethyl ether. Before I'm moving on to the solution, let's see. In your diethyl ether, you have CH3, CH2O. Let's see, in our ethanol, CH3, CH2O. So in this case, your 2 molecules, they look like similar. Therefore, diethyl ether molecules interact with your methanol through the dipole intermolecular forces, and also you also have London dispersion. Therefore, the ethanol dissolves diethyl ether much more. Your water, you can form some hydrogen bond. In this case, your diisoether has a polar bond, but it's not a polar molecule. In this case, that dispersion forces is weaker. That's about the prediction of your solubility. Solubility is going to be affected on the temperature, on the pressure, particularly for your solid. If you have your solid, your pressure influence is negligible. Your temperature is the major impact factor. You have three types of compounds. One of them, increase the temperature, your solubility increases. Maybe linear, maybe exponential, such as potassium chloride, potassium nitrate, sodium nitrate. Second group, such as sodium chloride, temperature increase from 0 Celsius to 100 Celsius. Your solubility changes very insignificantly. Solubility changes very, very slightly. Another group, such as this cesium sulfate, so your solubility from 0 decreases slowly and then stays. So this is your third possibilities. Some chemicals, some ionic compounds is going to subject to the decrease in solubility when you increase the temperature. The pressure influence normally influencing on the gas. If you increase the pressure, generally speaking, the gases are going to be more soluble. Gas molecules dissolve more when you increase the temperature. When you increase the pressure, Restate, pressure affects on the solubility of the gas. The gas solubility increases with the higher pressure. The pressure increase, the more gas particles is going to be colliding with the liquid surface. Therefore, more particles will be dissolved at equilibrium. Whenever the equilibrium is re-established, more particles will be dissolved. About the temperature influencing, if you increase the temperature, the gas dissolves less. The reason is when temperature increases, your gas moves faster. The thermal motion becomes stronger. So they are escaping from your surface of the liquid. Solubility decreases. So how do you determine the solubility of the gas? Solubility of the solid is complicated. So we need a further study because there is something called insoluble and soluble. Later on, if you go to the chemistry 2, you are going to further study equilibrium and the solubility rules. About the solubility of your gases, we use the Henry's law to determine it. The Henry's law states solubility of a gas, S gas, is directly proportional to the partial pressure of the gas above the solution. The equation is solubility equals the KH multiplied by the partial pressure for that gas. This gas is whatever you are going to study. For example, we are going to determine the solubility of carbon dioxide in your Coke. The partial pressure of the carbon dioxide gases inside of a bottle of your cola is 4 atm at 25 Celsius. Whenever you open the can, you heard zzz, right? And you see gas comes out. That's carbon dioxide because the partial pressure inside is 4 atm, much higher than the partial pressure of the atmosphere, 1 atm. The question is, what is the molar solubility of CO2? At 25 Celsius, the carbon dioxide has a Henry's constant, KH. KH, Henry's constant, which is 3.3 times 10 to negative 2 moles per liter per ATM? This question is pretty simple. You are going to determine your plan, determine the partial pressure is already measured for ATM. You need the value of KH, which is also measured, is already determined. And then you simply use the Henry's law. So Henry's law states the solubility of your gas is directly proportional to the partial pressure of that gas above the solution. Our solution will be solubility equals Henry's constant, 3.3 times 10 to negative 2 moles per liter per ATM multiplied by 4 ATM. You determine the molar solubility. Then followed by, we are going to discuss the concentrations definitions. Your concentration usually can be expressed in 5 different ways. First one called molar concentration. Second one called molar concentration is called molarity. Second one called molality. Be careful, these two, molarity, molality. And you also have parts by mass, parts by volume, mole fraction. In terms of the molarity, this molarity defines as the moles of your solute divided by the total volume of solution in liters, moles per liter. You use capital M to denote it. Your molality, smaller m, is defined as the moles of your solute divided by kilograms of your solvent. Make sure this is the kilograms of the solvent, not kilograms of solution. Solvent only. Parts per mass, you use the mass of your solute divided by mass of your solution. This parts per mass by itself usually is unitless. Sometimes you use ppb, ppm. ppm means parts per million, 10 to the power negative 6. ppb, parts per billion, 10 to the negative 9. And also you have something called parts by volume. You use the volume of your solute divided by total volume of your solution. The mole fraction, capital X, you use moles of your solute divided by the total moles of your solute and solvent. You calculate the moles of your solute, calculate the moles of solvent. You add them together. That's the total moles of your solution. So this mole fraction is also a unitless value. It's a fraction. Let's practice. Calculate the molality. Our problem is, what is the molality of a solution? In this solution, you dissolve 32 grams of calcium chloride in 271 grams of water. What's our plan? Our plan, first one, you need to define the molality. Molality is defined as the moles of your solute, in this case CaCl2, divided by kilograms of your solvent, water. You need to convert the mass of a calcium chloride into moles. So you use mass divided by the molar mass of calcium chloride. And then you also need to convert grams of water, 271, to kilograms. So you divide it by 1,000. Convert kilograms to kilo. And then you simply use the definition molality equals to the moles of your solute divided by the kilograms of water. Our solution. Step 1. Convert your 32 grams of calcium chloride into moles. Your molar mass of calcium chloride can be calculated by adding calcium molar mass and chlorine molar mass, atomic mass. So my calculation, 0.288 moles per 0.288 moles of your calcium chloride. molality equals to the moles of chloride, calcium chloride, divided by kilograms of water. You use your 271 divided by 1,000. So you determine the molality, which is 1.06 smaller m, because moles per kilogram. We are going to learn how to interconvert concentration terms. You can convert your concentration terms based on the moles. Remember, your moles is very critical to you. If you want to convert moles to mass, you need your molar mass. And you also need to convert the term based on the mass to the ones based on the volume. You need the density. The mass divided by density give you the volumes. Be careful, when you calculate the mass divided by density gives the volume, that volume is impossibly in milliliters. In your molarity, you need liters. Don't forget to convert milliliters to liters. Your molality involves in the quantity of your solvent. On the other hand, so the concentration terms by the molarity, moles, parts per million, parts per billion, parts by mass, parts by volume, they are involved in the quantity of your solution. Be careful, molality, you need kilograms of your solvent. Other terms, make sure you have that quantity of your solution, either liters or moles or mass. So be careful with these differences. Let's interconvert the concentrations of hydrogen peroxide from 30% to molarity to molality to mole fraction. So here we have the question. You have your hydrogen peroxide, H2O2, which is a very powerful oxidizing agent used in concentrated solution and also can be used in the rocket fuels. So when you dilute it, so you can use it as a higher bleach. What we know, an aqueous solution of hydrogen peroxide is 30% by mass. 30% by mass. This solution, aqueous solution of your hydrogen peroxide, has a density 1.11 grams per milliliter. Our question, calculate its molality, smaller m, mole fraction, capital X, molarity, capital M. What's our plan? First of all, you need to find the mass of the solvent. You need to know how many grams of water, how many grams of your solute as well. So in that case, my suggestion is you assume you have 100 grams of solution. Therefore, you calculate the mass of your solvent, the mass of your solute in 100 grams of solution. And then you take the differences in the mass of solute and the solvent for the mass of your peroxide. And then if you have your solute hydrogen peroxide, you convert the mass into the moles. Your solute, similarly, solute solvent, you can calculate the moles. And then you determine the mole fraction. For your molarity, you do need the volume of solutions. You use the mass, you assume is 100 grams, use the mass divided by the density. Again, don't forget to convert milliliters of the, liters. Our solution for your question A, molality calculation. First of all, you assume you have 100 grams, therefore your water, you use 100 grams. Your hydrogen peroxide will be 30 grams, right? Totally you have 100 grams. Your hydrogen peroxide is 30 grams. Your water will be 70 grams. You convert 70 grams to 0.07 kilograms divided by 1,000, and your hydrogen peroxide, you use your molar mass divided by its molar mass. Molar mass for hydrogen peroxide 34.02, and then you determine its moles. You use the moles divided by kilograms of your water. My calculation is 12.6 molarity of your hydrogen peroxide. Second question, you want to determine the mole fraction. Therefore, you need the moles of your hydrogen peroxide and the moles of your water. Moles of water, you can use 70 grams divided by its molar mass, 18.02. You determine the moles. And then mole fraction, you use the hydrogen peroxide, 0.88 divided by total moles. The mole fraction for hydrogen peroxide, 0.185. The C, about the molarity, so you need the liters. So you use your mass divided by density, calculate 90.1 milliliters. And then you convert to liters. You use 0.882 divided by the liters. Sorry for that. The answer, you determine it by yourself. Another very important topic is about colligative properties of solution. Next class, we are going to calculate 4 different colligative properties of your solution. Colligative properties are the properties. Usually they are physical properties that depend on the number of solute particles, not their chemical identities. The number of the particles in your solution can be predicted from the formula and the types of solute. If you have ionic compound, they are soluble in solution, they can break down. You have 2 types of compound. Technically, you have 3 types of solute called strong electrolyte, weak electrolyte, and also you have non-electrolyte. The strong electrolyte dissolves and completely dissociated. The weak electrolyte dissociated but dissolved partially. So your non-electrolyte, meaning they are not going to be dissociated. This non-electrolyte, usually if you have 1 mole of your particles, so dissolved in your solution, that particle stays as itself. So again, to repeat, the colligative properties is the properties of your solutions. Colligative properties are the properties depending on the numbers of your solute particle. The number of the particles in your solution can be predicted based on the formula and the types of your solute. Electrolyte separates into the ions when they dissolved in water. Strong electrolyte dissociates completely. So otherwise, the weak electrolyte dissociate, breaks down very little. Non-electrolyte does not dissociate, meaning the non-electrolyte, so that 1 mole of the dissolved compound but not dissociated yields 1 mole particles in your solution. So we are going to do the calculations. So the calculations will be 4 different of them. So one is called vapor pressure lowering. Vapor pressure lowering, delta P can be calculated using Rao's law. Second one called boiling point elevation. Second colligative property, boiling point elevation, meaning if you form a solution, your boiling point for the solution will be higher than the pure solvent. For example, your water at 180 m, the boiling point is 100. If you produce a solution, boiling point will be higher than 100 Celsius. And also you have third property called the freezing point depression. Similarly, for your water, freezing point is 0. When you form a solution, the freezing point will be smaller than 0, will be negative. So boiling point elevation delta TB equals to KB multiplied by your molality. Be careful, this is molality. Freezing point depression delta TF equals to KF multiplied by molality. KB, KF, they are the constant values, can be found, but just be careful. KB and KF, they are different. The last colligative property is called osmotic pressure. Osmotic pressure equals to the molarity multiplied by RT. Molarity is your solution concentration. R is your ideal gas constant. You use 0.08216 atm liter per mole per Kelvin. Temperature, make sure is in Kelvin. If you have a solution which is composed of strong electrolyte, in this case, you need to do a justification. You use the 1/2 factor to adjust the vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Everything essentially similar to this we call the non-electrolyte solution. You also call it ideal solution. This ideal solution, so you have these 4 variables, 4 properties, and you just simply use a 1/2 factor, I to adjust it. So these different properties, we are going to discuss it in the next class. We are going to do this calculation. And before we learn the strong electrolyte, how do you calculate 1/2 factor? 1/2 factor is going to be calculated by the measured value of your electrolyte solution divided by the expected value for the non-electrolyte solution. For example, sodium chloride. You assume sodium chloride is not going to be breakdown. If you assume you have 1 mole, this is the expected value for the non-electrolyte. And your sodium chloride breaks down to 1 mole sodium, 1 mole chloride. 1 plus 1, it will be 2 moles of the dissolved ions. 2 divided by 1, that's the 1/2 factor for your sodium chloride. Also, next class, we are going to do the calculations. And then followed by is different types of colloid. The colloid, you have aerosol, 2 types of aerosols. One is your liquid dispersed in your gas, such as the fog. Second one, aerosol, is your solid dispersed in the gas, is your smoke. And then you can have your foam, the foam, such as your gas dispersed in your liquid, such as that whipped cream. I believe in your birthday party, you write it down happy birthday, so that whipped cream, you disperse gas into the liquid. Solid foam, you dispersed in the solid, such as your marshmallow. I think you love that little thing. And then you have emulsion, liquid dispersed in liquid. This is commonly used milk, soy milk, or the milk. Solid emulsion is your butter, such as your butter. You disperse your liquid into the solid. It's called butter. You have another one called the sol. You disperse your solid into the liquid, such as the paint, such as our human cell fluid. Cell, not only human cell, the cell fluid. You have solid sol, solid dispersed in solid, such as the opal. So the colloids usually show the 2 types of properties. One is called the light scattering, also called the Dando effect. Dando effect. Dando effect tells you, so the narrow, barely visible light beam can pass through a solution. If you have a solution, this visible light passing through, but the visible light is going to be scattered and broadened by passing through a colloid. The second one, in this A, you have first one, this is solution. When the light goes through, the light passes through. When the second one, the light goes through your colloid, you see the light scattered, you see a broadened pathway. Sometimes when you go back home to your house, so you see the sunlight, you see the beams of the sunlight, meaning in your house you have lots of dust. So that dust is an aerosol, scattered your particles. The Dendel effect is light scattering by the particles in your colloid or a very fine suspension. The intensity of the scattered light is inversely proportional to the force power of the wavelengths. The larger the wavelengths, the weaker the intensity is. The blue light is scattered much strongly than the red light because your blue light has a shorter wavelengths, such as 474 nanometers. Your red light may be 750 nanometers. The blue color sometimes can be seen in the smoke emitted by your motorcycle. The second property called Brownian motion. Brownian motion, also called padicis, named after a very famous botanist, Robert Brown. Brownian motion of a particle suspended in your fluid, so resulting in their collision with the fast-moving molecules in your fluid. So you have alteration of the particle position inside of your fluid. In your fluid, you have subdomain, relocation to another subdomain, followed by more fluctuation in a closed volume. So this random erratic motion is called Brownian motion. So the kinetic energy of the molecule, Brownian motion, so together with the molecule rotation and vibration, so you can calculate them as the fluid internal energies. So at this point, I'm going to finish today's lecture. Next class, we are going to finish your chapter 13, part B, calculations of the colligative properties for your solution. You have 4 different colligative properties. We are going to discuss them in the next class. Thank you so very much. You have a wonderful day.